Lecture 5, 1 degree of freedom vibration under general forcing. At the end of this section, you should be able to form closed-form solutions for functions that are periodic but not purely harmonic, and also aperiodic functions. So in this case, we're going to be looking at impulse, step, and ramp functions, and then combinations of those three. Compared to what we did in the last section, we are now going to generalize the type of forcing we are going to have on the right-hand side of our equation of motion. In the previous section, we could only have a single sine function or a single cosine function. But real functions could be periodic but not simple harmonic. They could also not be periodic at all, and they could be made up of harmonic functions or maybe not made up of harmonic functions. So real-world forcing can be much more complicated than the limited types of forcing we looked at in the previous section. But these more complicated functions might be made up of multiple harmonic functions, multiple sines and multiple cosines. In which case, we know the general way to solve those types of systems where we have a single sine or a single cosine. What we're going to do with multiple sines, multiple cosines, is solve for each term individually and superimpose all of our solutions together. And that works great if the right-hand side is made up of a bunch of sine and or cosine functions, but again, real forcing functions are more complicated than that. In fact, we could have a right-hand side that is non-harmonic. No sines, no cosines appear, but it is periodic. It's going to repeat itself over and over again. Or maybe it's aperiodic and it doesn't repeat at all. So knowing the solution for a cosine or a sine doesn't seem like it's quite enough, except we are going to use Fourier series on our forcing functions. And as we remember with the Fourier series, it's going to let us turn any function into an infinite series of sines and cosines. So in general, with the second order systems, 1 degree of freedom, we are going to see our left-hand side have mass, damping, and a spring constant. So we have an x double dot, an x dot, and an x term, like we've been seeing for multiple sections now. And the right side is just this generic f of t. It's some forcing that's a function of time. So any time-dependent function, it doesn't have to be a cosine or a sine like in the last section. We're now generalizing what we were looking at previously. So the idea we're going to use here is that we can expand this f of t into its Fourier series representation. So we can rewrite the right-hand side exactly as that constant term plus an infinite number of cosine terms plus an infinite number of sine terms. And this goes back to what we did in the first section when we were looking at Fourier series expansion of continuous functions. So we already know from there how to find the a naught, how to find the an's, and how to find the bn's for any function f of t. So it looks like we've made the right-hand side much more complicated, and in a sense we did. However, solving now for x of t, solving this second-order differential equation, is now going to be much easier because we already know from the previous section how to find the particular solution when we have a cosine term or a sine term. Here we have a lot of cosine terms and a lot of sine terms, and we have a constant, which is also fairly easy to find the particular solution for. So one at a time, we can find particular solutions to every piece on the right-hand side, put it into the left-hand side to get a piece of our particular solution, and then we can add them all up to get the entire particular solution. Once we have the particular solution, then we can combine that with the homogeneous solution, which we've already seen in the previous sections for the left-hand side, apply our initial conditions, and get our total solution for x of t. How do we do it term by term to find the pieces of our particular function? So we're going to start by looking at just the constant term. So I've simplified the right-hand side. I'm only looking at that a naught over 2 piece, and I'll look at the cosine terms and then the sine terms. So for this part of the particular solution, we are going to have this constant on the right-hand side. When we let that constant go through the left-hand side and equate them, we find that the particular solution for this piece, we get a naught over 2k. And this will happen because when we put in just say a for our x of t, we're going to have k times that a, and then the x dot is going to go away because a constant's derivative is 0, and its second derivative is 0. So that's where this a naught over 2k is coming from. So the strategies we're using here are just what you learned in your ordinary differential equations class for solving for particular solutions using assumed solutions. I'm not going to go through all the detail of the derivation of these, as we did it a little bit before in the previous section, and you've done it in your ODE class. Then we can look at the cosine terms. So on the right-hand side, I'll just have one of our infinite cosine terms. I'll have the nth cosine term in that series. And if we can solve it for the nth one, we can solve it for any of them. Right, so the nth term is going to have that an coefficient, which we solve using the Fourier series expansion of that f of t. Right, so our assumed solution would be in the form of either a sine term plus a cosine term, or, like we see here, our assumed solution is in the form of a cosine term with a phase difference. Again, won't go through all the details, but if we put an assumed solution into that left-hand side and equate them, this is the expression we get for the nth piece of our particular solution for the nth cosine term. So if we see what's happening here, for the nth term, it will use the coefficient that we found from the Fourier series. It'll have the cosine term, but now we have a phase, this phi sub n. We'll look at that on the next slide. And then on the denominator, we have a combination of different parameters in our system that use m, c, and k. So we have that n coming back if we're talking about the nth term. We have this r, which we'll look at on the next slide. And the damping ratio is going to come into play as well. So depending on how many terms we're going to use of cosine and sine functions, we'll have that many terms in our particular solution. And then the sine terms. Again, just looking at the nth sine term here, we have that b sub n coefficient that we have already found by expanding f of t, and we see a very similar looking particular solution for the nth sine term. So you use that coefficient we already found, that same phase we're about to calculate, this r ratio that will be on the next slide, and so on. So it basically looks the same as the cosine terms, but the coefficient is different, and it's a sine versus a cosine. Now, so we went through that quickly, but these are just the pieces of the particular solution that we're going to be putting together to get the total solution. So before we start putting it together, we need to see what is the definition of this phase, of the nth phase angle, and what is this r. So here we see how I calculate the nth phase, and this will correspond to our an and our bn, or the nth cosine term and the nth sine term. So we're going to use that 4-quadrant tangent of that expression, where omega is going to be the fundamental frequency of our forcing function. So omega, this is akin to the driving frequency, but this is coming from doing that Fourier series expansion. And actually the definition of omega is exactly what we used before when we did a Fourier series expansion. It was 2 pi over t, that smallest period that repeats itself. And this r that comes up when we compute our phase angle, and it comes up when we compute the particular solutions for the sine and the cosine, r is just the ratio of this fundamental driving frequency to our natural frequency. So going back a moment, that's where this r and this phi are going to come into play. So we're going to calculate a lot of pieces of our particular solution and put them together. Always we want the constant term, and then we're going to select how many cosine terms, how many sine terms to use, so how many values of n to use, and put together in forming our complete particular solution. So when we put them together, we have the constant term plus, and now since they shared a denominator, the cosine terms and the sine terms of the particular solution did, I just put it over one common denominator here, and we can see that this forms our complete particular solution. And if we actually use an infinite number of terms here, it is exactly equal to the particular solution. In practice though, just like we saw when we did Fourier series expansion, we can't use an infinite number of terms. We are going to have to truncate it at some point. So we might use 10, 100, 1,000 terms to get a pretty good approximation to our particular solution, and we'll be able to see through convergence when we've used a sufficient number of terms such that the error we're getting is pretty small. And keep in mind, this is just the particular solution to these forced functions. We will still have to worry about the homogeneous solution and then the total solution next. We can take this particular solution and we can differentiate it with respect to time. And this will be necessary when we're applying our initial conditions. So our constant term is going to drop out, the cosine is going to go to negative sine, the sine will go to positive cosine, and we're going to have to use the chain rule as well. So this is the time derivative of our particular solution. Now we can put it all together to get the total solution. So our x of t total solution is made up of this particular solution that we were just looking at, which includes the constant term and then this infinite sum, and it includes the homogeneous solution. I didn't take time to derive this again. It's exactly the same as we saw in the last two sections when we had the simple harmonic forcing and when we had a free damped system. That's exactly the homogeneous solution that we were seeing. Now we're going to have to see what the x naught and the phi naught are. Those are going to come from our two initial conditions, our initial position and our initial velocity. So if this is our x of t, we can take it and we can take the derivative of it and we can get x dot of t. Now, we get fairly complicated results here. We're not going to get a nice clean definition for the x naught and the phi naught like we did in the previous sections because our particular solution is very complex. And depending on how many terms we use of our particular solution is going to influence what x naught and phi naught are. So since we have our definition of x of t and x dot of t, we can use those two algebraic equations, our initial position, our initial velocity, and solve for two unknowns, the x naught and the phi naught. Now this is not trivial to do because we have to evaluate this probably lengthy particular solution for each of them. And as I just said, depending on how many terms we use, the particular part of this could be slightly bigger, slightly smaller. It will eventually converge, but we need to know how many terms to use because that will influence the x naught and the phi naught that we find. Now, I will be presenting a numeric solution to this, to finding that x naught and phi naught, but there are other methods available to find out what they are. So once we find the x naught and the phi naught, then we can plug those into these two equations, and we do have the complete closed form solution to our x of t and our x dot of t. But again, we want to note these closed form solutions, when we find an x naught and a phi naught, we cannot any longer use an infinite sum here. The x naught and phi naught were based on truncating the sum at some value, and then that will become our entire x of t or x dot of t expression.